Okay, so hello everyone. Can you hear me well?
Yes, we can hear you.
Yeah. Okay, so last Monday we introduced the whole class, like the course structure and some detailed information about what we're gonna cover in this class. So today we're gonna move to the first session of the background. We're gonna learn how to analyze a feedforward neural network and how we do verifications for feedforward neural network. So that's our main focus today. And oh, what's going on? Okay. So we're gonna learn about the reachability analysis methods. That's used for verifications for feedforward neural network. And then we're gonna basically learn about the concept. Sorry. So we first introduce what is the feedforward neural network and how does a feedforward neural network work. And then I introduced the concept of reachability and verification. So basically, we're gonna learn what is the reachability analysis of a feedforward neural network and what is the verifications of feedforward neural network. Okay, and then we're gonna learn the first approach for verification of feedforward neural network. So that's called Polyhedron approach. So we're gonna learn the core step in reachability analysis of our feedforward neural network, and then we learn a fundamental backgrounds on Polytope, and then I'm gonna introduce to you the MBT toolbox and the NNV toolbox and how we install NNV and MBT toolbox. So basically, MBT toolbox is a subcomponent in NNV. So NNV use MBT toolbox for visualization and manipulate Polyhedron in the reachability analysis of a feedforward neural network. And then you're gonna learn via several videos how to use MBT toolbox in NNV to construct and manipulate a polytope. So after you master how to do that, then we're gonna use polytope to compute the reachable set of a single layer in a feedforward neural network. And I'm gonna show you that basically to do the analysis of a feedforward neural networks, the core computations reduce to how to compute the reachable set for a single layer that have a convex input set. Okay, so you're gonna learn the core computation in the reachability analysis of feedforward neural networks using Polytope in this talk. So let's get started. What's going on? So what is the feedforward neural network? So I believe many of you already know what is a feedforward neural network. So it's the simplest artificial intelligence network that's innovated long times ago. And it consists of input layers, many hidden layers, and an output layer. And hidden layers have multiple neurons. Okay, and neurons on one layer are connected with its preceding layer using weights. And the information flows in the neural networks in one direction, just forwardly. So from the input nodes through hidden nodes to the output nodes. Okay, so that's why it's called feedforward neural network. Okay, and in this example, this figure, you see we have a very simple feedforward neural network with one input layer, one hidden layer, and one output layer. And then the neuron in the hidden layers is connect with the input layers via waves. Okay, so here's waves, and waves you have some value for the waves. Sorry, is there any questions?
So I have one question. So what does the number mean? So there are 2, 0, -1, 1. What does that mean?
So that means, okay, so if you have the value x1 and x2, right? And then the value of this neuron, the first neuron in the hidden layer, is equal to 2x1 plus 0x2 before you apply the activation function on that neuron. Okay, so that's mean the way. Yes,
so
what I mean?
like the second neuron in the second hidden layer is that means 1x1 plus -1 times x2, right?
Yes. And
Okay.
then I haven't talked about the activation function yet. Okay, so that's the value of, that's the input value to this neuron, and then the output is the value after you apply an activation function on that's input. Okay, so that means the input to the first neurons equal to 2x1 plus 0x2. The input to the second neuron of the hidden layers equal to x1 minus x2. And the input to the last neuron of the hidden layers equal to 1x1 plus x2. That's clear?
Yeah, that's clear. Thanks.
Okay. And similar happen for the neuron at the output layer. Okay. So the input to the first neuron of the output layers equal to minus the output value of the first neuron of the hidden layers plus 0 value of the output of the second neuron of the hidden layer. So and so on. Okay. Any other questions? Okay, good. So okay, so now how we evaluate our feedforward neural network. Okay, so feedforward neural network is formally defined on 3 components. The first is the wave matrices. So the connection between the hidden layers, or the hidden layer with the input layer, or the output layer with the hidden layers, defined based on the wave matrices. Here you can see W, K, or K minus 1. That means the connection between the current layer with its previous layer. Okay, and then the bias factor BK as each layer K. And then the activation functions FK. So that means when you have the input to a specific neuron, defined based on the weight and the bias, and then you're gonna apply the activation function on that neuron to get the output of that neuron. And you're gonna have different types of activation functions. So you can have sigmoid, tanh ReLU, lead key ReLU, or max out, or ELU. Okay, and the most popular one that we're gonna consider in this class is gonna be ReLU, tanh and sigmoid, which is the very popular activation functions used in the real world. Okay, and then the output of the ith neuron in the end neuron layer is defined by this. Okay, so that means you get the input of that neuron, plug the bias at that neuron, okay? And then you sum all of them, and then you apply the activation function, and then you get the output of that neuron. Is there any questions here?
Will these slides be uploaded after the class?
Yes, of course. I'm gonna upload this slide and the video I record in this class.
Thank you.
Yeah, okay. So no questions so far? Okay, great. Okay, so this is an example how we evaluate a feedforward neural network. Okay, so now you have two inputs, X1, X2. If I give this input a specific value, I want to compute the output of the network. Okay, so and from this one you can construct the way. Okay, the way matrix. The way matrices between layers. So we have the way 2, 1, which is the connection between the hidden layer with the input layer, and the way 3, 2, which is the connection between the output layer with the hidden layer. And you from these ways you can construct this matrix, these matrices. Okay. And then suppose we have the bias for each layer. So we have B2 and B2 right like this, okay? And now if we have the input vector is X1, X2 equal to 1, 1. So what is the input, what is the output at the hidden layer? So suppose here we have the activation function for the hidden layers, and the output layer is value, okay? So first we compute the input to all the neurons of the hidden layers here. W2, 1 times X plus B2, okay? And then you apply the value activation function on that input vector, okay? So compute the input to the hidden layers, you're gonna have this matrix multiplied with the input vector plus the bias B2, and then you get this, right? And this is the input vector to the hidden layer. So the input to the first neuron of the hidden layer is 2.5. The input to the second neurons of the hidden layer is -1. And the input to the last neuron of the hidden layer is 1.5, okay? And then you're gonna apply the value on that input, okay? So when you apply the value on that input, you see, so you know that the value, back a little bit, sorry. Here's, so the value activation function defined based on max between 0 and X. That means if X is smaller than 0, then the output is gonna be 0. If X is larger than 0, then the output is gonna be equal to the input. So that's the value activation function, okay? Okay, so now we apply the value on the input of the second neuron, so which is -1. So we got 0 here, and then we apply for the last input of the hidden of the neuron of the last neuron. So we got the results 1.5. Okay. So any questions so far?
I have one question. So how do you decide the bias vector?
So no, we don't decide the bias vector. Okay, the bias vector is come up in the training process, right? When you train, actually you're gonna train the weight and the bias. Okay.
Okay, that makes sense.
Okay. So when you train, you update the weight and the bias to make sure that the network give you the accurate answer. So in training process, you're gonna get the W and B. So we just assume that our network have this way matrices and these bias factors.
Yep.
That's clear?
Yeah, that's clear.
Okay. Thank you for question. Just jump in and ask question, okay? I want to make everything clear. Okay, so now we compute the output of the output layers. Okay, so we want to compute y equal to y1 or y2, which is the output of the output layers, L3 here. So the same thing happened here. We compute the input to the output layer, and then we apply the value activation function on that input factor, and then we get the result. So the result gonna be 0 and 3. So you can check it if you want. Okay. So you can see that the output of the hidden layers is the input to the output layer, and then you can do it again and again to get the output of the network. So that's how we evaluate a feedforward network given a specific input vector. Okay. So now we introduce the concept of reachability and verifications. So what is the reachability analysis of a feedforward neural network, and what is the feedforward neural network verification? Okay. So now you have this example again, and if you have a single point input, you evaluate, you got a single output point, right? And then the same, when you get another input point, you get another output point. And you get a bunch of input points, you get a bunch of output points corresponding to that input vectors, right? So the reachability problem here is that if you have, instead of input vectors, you have an input set, which is a set contain infinite number of input points. How we can construct the output set of the feedforward neural network that contain all possible output corresponding to all input points in the input set here, right? So the reachability of a feedforward neural network is that given a convex input set, how to compute the output set of a feedforward neural network. So that's the core questions for reachability analysis of feedforward neural network. Okay. And what is the verification? So suppose you have an input set and you have a neural network F, then you compute the output set of the neural network. And then you have a set of property, like for example, a property P defined based on the output of the network. Okay. So the property P is a predicate over the output space of the network, right? And then you want to reason whether or not the output set intersect with the property P. Okay. So if the output set intersect with property P, you say the network satisfy the property P, and you can give or you can assign some specific input form that gives you the fact that the output of the network satisfy the property P. Okay. And if the output set do not reach the property P, then you say the output set do not satisfy the property P. Okay, so you can think in terms of safety property. So if the property P is unsafe regions, that's you don't want your neural networks reach to, right? You don't want the output set reach the unsafe regions. So if the output set do not reach the unsafe region, then you say the network is safe. Otherwise, unsafe, right? So it's clear.
I had one question. That
Okay.
all makes sense. So, well, I guess two questions. The first being, are there instances where we would say want a property P to apply to every value in an output set?
Yes, corresponding to the input set.
Right. So, for example, we would almost do kind of like the inverse of what you're saying, where we want to make sure that there are no values from the output set which do not have some safety property P.
Mm-hmm.
Okay. Second question then, can you give an example of what these property P's consist of? Because I'm thinking about this output set as a series of values. So would property P consist of some constraint against the output values that we would see?
Yes, yes, that's correct. So basically, the property B is gonna be a set of constraints, right? You can imagine it's like a linear constraint. So in this class, we're gonna focus on linear constraint. Okay. So that means the output of the network need to satisfy some linear constraint or something like that. And here we use set to visualize that. Right? If you have a set of constraints, you can visualize a set, right?
Right.
And then also the output set should be a bunch of constraints on the output, right? And then you check these constraints collide with each other or not. So that's the idea, right?
Okay.
That's clear?
Would one property, for example, could you say that guaranteeing that a certain data type would be able to properly give you the degree of precision that you'd need from an output set? Would that be kind of in the same vein, or would that be more, would that be outside of, I'm trying to.
Yeah, so you try to get an example, right?
Mm-hmm.
For this kind of property. Okay, so let me use one example. So if you train a neural network that you want, okay, so there are a bunch of networks trained on the autonomous, no, the aircraft, autonomous aircraft. Okay, so they depends on the input set, which is describe the condition of the environment. Then the autograph need to figure out that's whether it's in clear conflict condition or it need to turn left or turn right, something like that. Okay, so that's the output, right? The output of the neural network is going to be clear of conflict, or turn left action, turn right action, or turn quick left, or turn quick right, something like that, right? And then when you have another aircraft approach your aircraft, okay, and then you want to make sure that in that case the clear of conflict never be the minimal one, because if this is the minimal one, then your system gonna take the clear of conflict as a command, right? And then it's gonna collide with the other aircraft, something like that. So that means you can define that the clear of conflicts never be a minimal command in this case, and you can describe that's like a set of constraints, right? That means the clear of conflict need to be larger than the other, like turn left, turn right.
Right. That makes sense.
Something like that, right? You're gonna have a set of constraints on the output set, something like that. That's clear?
Yes.
Okay. Okay. Thank you. So, so that's the concept of verification for feedforward neural network.
So I have one question. So the verification problem, does it mean that you want every output to satisfy this predicate P? Is that the meaning of verification, that you want to make sure that everything in the output set satisfy the property P?
No, no, no. I don't mean that. Okay. So only a subset of the output set satisfy the property P. Then I say, okay, the neural network is satisfy the property P. And then I give some example for that.
I see. Okay, so this is a much right. So it's you don't require that every output must satisfy P. You just require as long as there's some output that satisfy P.
Yeah, it's
Okay.
very
Okay.
yeah, it's very similar to like SAS problem, right?
Okay.
Yeah. Okay. Okay. Thank you for the questions. Okay, so now we understand how the feedforward neural network work, and then what is the reachability problem, and what is the verification problem of feedforward neural network. Now I'm gonna introduce the first approach, or polyhedron approach, and I'm gonna show you what is the core steps that you need to use to compute the reachable set of a feedforward neural network. Okay. And then to do these steps, you need to learn a fundamental background on Polytope. Okay, so basically, what kind of tools you need to use and what kind of core operations you need to use to be able to compute the reachable set of a feedforward neural network given a convex input set. Okay, and then I'm going to show you how to use MBT toolbox in NNP to perform some basic operations on polytopes, how to construct a polytope, how you do affine mapping or intersection, or how to check emptiness or boundness of a polytope. All of these operations are the core operations that you need to use for reachability analysis and verification of a feedforward neural network. Okay, and then finally, I'm gonna use a polytope to compute a reachable set of a single layer. And I use a very small example, just two-dimensional example to do it, to show it. Okay. Any questions until now? Okay, good. So let's go. Okay, so the polytope approach, given that we have the input set, which is a union of polyhedron, complex polyhedron, and then you have a feedforward neural network you already trained, okay? Then you want to compute the output set, Fi, which is basically it's also a union of another polytopes, a union of polyhedron. It's very complex, okay? And then I remind the activation function, ReLU. So we consider ReLU here. We also can extend this word for nonlinear activation function like tanh and sigmoid. So you're gonna learn it via the star set approach. I'm gonna introduce later, okay? And then the neural networks can be seen as a set of layers, L1 to Lk here. It's an array of layers, object, okay? And then the reachable set of the network can be defined recursively like this, okay? So if you have a k layers, L1 to Lk, then the reachable set is the output set of the layer k, okay? And the output set of the layer k is defined based on this equation, right? And the output set of the layer k defined based on the output set of the layer k minus 1, okay? And the output set of the layer k minus 1 is defined based on the previous layers like k minus 2 or something until k equal to 1, okay? So that's how you define the output set or the reachable set of the neural network in a recursive manner, okay? Come on. Okay, so now we assume that we only have a single input set, which is a convex polyhedron. And how we gonna compute the output set of the network. So the approach here is that we can do layer by layer computation, right? The output set of the first layer is going to be the input set of the second layers, and so on until the last layer. So that means the core computation, the core reachable set computation, is how to compute the reachable set for a single layer. Okay? So given a convex polyhedron input set, how to compute the reachable set for a single layer. Okay? And that layer might have like n neurons, something like that. So to do that, we need to compute the input to this neuron, right? Okay, using the weight and the weight matrix and the bias vector of that layer. Okay, we need to compute the input set to this neuron, right? And then you need to somehow apply the value activation function on the input set you get. Okay, so that means is have the first core step is that how you compute the input set to the neuron of the layer, okay, using a weight and the bias matrix. And you can see when you have I is a polyhedron, then this equation equivalent to the R5 mapping operation of the polyhedron, right? So when I is a set, then you're gonna get the R5 mapping of that set, okay? And then the second step is how to apply the step value operation on a polyhedron you got, okay? Separate these two steps. This is core steps that you need to do to be able to compute the reachable set for a single layer. Okay, any questions? No questions?
Excuse me, I have one question. The output set, how does it get, how many forms do you get in the output set depending in the number of layers that you are working with?
Can you repeat the questions?
Yes, sure. So how does the output set look like depending on the number of layers that you are working with?
So yeah, thank you. So I'm gonna show you that for single layer, single input set, after single layer is gonna produce a bunch of output set, right? And this output set gonna be the input set to the next layer.
Okay.
Then the output set of the last layer is a union of convex polyhedron, right? So I'm gonna show you that in the worst case, even a feedforward neural network with n neuron, then in the worst case, it's gonna generate 2 power n polyhedron when you do exact analysis, right?
Okay, thank you.
Okay, so now you know that we use Polytope to do the reachable set computation. I'm gonna cover a very brief background on Polytope, and then I'm gonna introduce the tools that you can use to manipulate or create polyhedron and Polytope, and then do the computation. Okay. So what is the Polytope here? So Polytope is a geometric object with flat sides. So you can find it in Wiki. So here I put the embedded link. Then you can click it and you can read it from Wiki. Okay. So a generalization of any numbers of three-dimensional polyhedron. So here's like a little bit confusing when I say polyhedron and polytope, something like that. So basically in math, they call polyhedron is a three-dimensional polytope, okay? It's defined for three-dimensional polytope. However, in MBT toolbox, when you set polyhedron object, you can create like multi-dimensional polytope. So that's why I always mix up between polyhedron and polytope. But just keep in mind that polyhedron mathematically is three-dimensional polytope. However, in MBT toolbox, you use polyhedron class to construct a polytope in like as many dimensions you want. Okay, and then for two-dimensional, we call it a polygon. And then there are examples of a polygon here. You can see like a triangle, a rectangle, a very weird shape, something like this. And then here is a three-dimensional polytope, like polyhedron. Okay. So what is convex polytope? Okay. So in our class, we're gonna consider only convex polytope. And if you have non-convex polytope, you can split it up to a set, like a union of convex polytope. Okay, so you can have some like triangulation algorithm to do that. So that's another subject. So here we just assume that the input set is going to be a convex polytope. Okay, and convex polytope is a specific case of a polytope, and a convex set contained in n-dimensional Euclidean space. So a convex polytope may be bounded or unbounded. And here is an example for like 2D in 2D space. So when you have a convex set, what is convex set? So if you have 2 points and you connect 2 points by a segment, right? And all these points in these segments is inside the set. So that means it's called convex set. In non-convex case, when you connect 2 points, there are some cases that some point in that segment is not in the set, okay? And that's a non-convex set. And here is an example of convex polyhedron in 3D, okay? So any questions here? No questions? Okay, this is very basic, okay? Now, we're gonna introduce MBT toolbox called multi-parametric toolbox. So MBT is a MATLAB-based toolbox for parametric optimization, computational geometry, and model predictive control. So if you're working on the field of control or like control science, MBT toolbox is very popular. Okay, so it's developed from ETH Zurich. And in this class, we only focus on computational geometry in MBT toolbox. Okay, and what is the basic computational geometry we care about? And so first we need to construct a polyhedron, and then how we do affine mapping for a polyhedron, and then how you do intersection between two polyhedrons, right? So the intersection is very important. So if you want to check the safety of a feedforward neural network after you compute the reachable set, right? That means you have two sets, you need to check the intersection between the output set and the property, something like that. And then another less used operation is called compact whole. But I also introduce it here because I think it's a very important operations that you should know. And the compact whole operations can be used in closed loop manner, right? When you analyze or you compute the reachable set for a neural net control system, then you're gonna see we need to get the compact whole. However, the compact whole operation is very expensive, and in general, when we do the analysis for closed loop neural network control system, then we usually relax it's like interval hole or something like that. That means we only get the box that's contain two polyhedron, something like that. And then we also talk about the methods, the very important methods called is empty set. Methods will check the emptiness of a polyhedron, right? So when you get the intersection between two polyhedrons, you get another polyhedron, right? And then you need to check whether it's empty or not. If it's empty, that means there are no intersection between two polyhedrons, okay? And then another is bounded method. You check the boundedness of a polyhedron. So basically, it's not really relevant in our task here for reachability analysis of feedforward neural network, but again, it's still very useful. That you should know. And then another very useful method is called outer approach. So what this approach does? So this approach, this method find a smallest rectangle or box contain a polyhedron. Okay, and then finally is the plot method that you can use to visualize a polyhedron. Okay. Now how to install MBT. So basically, MBT is a subset of NNV. So when you install NNV, then you already have MBT inside, and then you can use it. Okay. So the requirement for NNV installation is that you need to have MATLAB 2019B or later, and hopefully all of you already have a MATLAB installed when you come to this class, because we're gonna have many code assignment, and maybe we're gonna have some days that we come together to solve some specific problem online. Okay, and we can discuss what is the problem, and you can learn it. Any questions so far?
I had one question. It's kind of more of a curiosity. Is it difficult to take a toolbox and get it published on the MATLAB add-on or apps, whatever they call their store, library viewer, the add-on explorer? Like, is it easier to make custom toolboxes and just keep them on GitHub than have them be distributed by MATLAB?
I don't think it's easy.
Okay.
I haven't done that before. I don't know, to be honest.
Okay. Yeah, I was doing some looking into it a while ago for a project, and it looked kind of tedious, but not bad. So I was just curious if there was a reason that you had it uploaded on GitHub versus in MATLAB's add-on library. So I thought maybe you'd run across it and I'd ask, but it doesn't.
So yeah.
As long as it runs.
Yeah, thank you for that. But you know, right now I believe some people in MATLAB they are very interested in NNV because we support deep learning toolbox. So basically, if you can anything in MATLAB using deep learning toolbox, you can bus the model, like the neural network model, into NNV and analyze very easily. In the future, I want to view NNV. Like I want to support like different architecture, different type of neural network, something like that, to make it like more popular. And then we can come up like another toolbox in MATLAB, like add-on toolbox, like you said. Yeah.
Cool.
Okay.
Cool.
So so NNV installation is very simple. So it's just 3 steps. You go to GitHub repository like called Trend Safe AI Lab. So basically, I'm in Nimbus, okay, and the reason I choose this name is because I need to have the name and the email to book my toolbox there. Okay. And I also have several other toolbox for CDS, but I haven't pushed it on this GitHub. But if you are interested, I think you can see it later. So now you just go to GitHub repository, clone NNV using git clone, and then you open install.m and install NNV. Okay, very simple. So here is video show you how to do it. Okay, so is there any questions for NMV installation? Oh, sorry. Can you hear me now?
Yes.
Okay, so I think I'm gonna post the video and the slide as well, so you can see the slide and you can see the video more clearly. Okay, sorry about that. Okay, so that's how we install NMV. Very easy. Okay, and hopefully next class you all have NMV installed before you come to this class, and we're gonna do some code assignment online too. Okay, just prepare for that.
I have a question. So like, can we install it on a server, like on the HPC, instead of installing it like on personal computer?
What do you mean by server?
Like the HPC, the high performance computing.
I haven't tried yet. Sorry about that. But I believe you can do it, right? Very easily. Just have MATLAB installed, and then you just install this in MATLAB. Like it's like an add-on toolbox, and then you can use it.
Yep. Thank you.
Okay, so let's move to. Oh, sorry. Okay, so now we talk about core computational geometry using MBT toolbox. So I'm gonna show you how to create a polyhedron object using polyhedron class in MBT toolbox. Then how you do R5 mapping for a polyhedron using R5 map. And then how you do intersection between two polyhedron using intersect methods. And then how to check if a polyhedron is empty or not using isEmpty set method. And then the compact hole of two polyhedron. And then check the boundness of the polyhedron using isBounded method. And then I show you how to find a smallest box containing a polyhedron, and then how to visualize a polyhedron using a plot method, which is very easy. And for more information, you can check the MPT toolbox user manual here. So basically, when you install NMD, it's gonna create the TPX manager folder, okay? And then in that folder, when you go down, you're gonna see MPT doc, and then in DOS, you're gonna see the manual of the MPT toolbox. So this manual, this user manual show you all the methods that support in MPT toolbox, and you can learn more in detail. However, what I cover in this class already enough for you to be able to use MPT to do reachable set computation for a feedforward neural network. Okay. Okay. So before we create a polyhedron object, so you need to know that a polyhedron object can be created in two forms. Okay. The first form is called hex representation, and the second is V representation. So what is hex representation? So hex representation, it just represents a polyhedron using inequalities or equalities. Okay, so we have two parts here. The first part is defined based on the metric A and B, which is the inequality part. And the second one is the equality part. So it's defined based on the metric AE and BE. Okay, and in V representation, so we can represent a polyhedron object using vertex and rays. Okay, so that is the formula how to represent a polyhedron using vertex and rays. And yeah, just here is a very simple figure. What is the ray mean? So if R prime is a ray of a polyhedron P, okay, and X is inside of P, then you have X plus the ray time with a coefficient gamma larger than 0, then this is also in P. Okay, so that's how a ray is defined. Okay, that's just a basic formulation for polyhedron representation. Okay, you can find more on the internet on Wikipedia. Now, in this video, I'm going to show you how to create a polyhedron object using MPT. Okay, hopefully you can hear well this time.
The sound is still bad. Can't hear anything.
Okay, so bad.
Can you try to share your screen and share your computer audio? Like there's an option on Zoom when you share your screen to allow for us to listen to your computer's audio. Maybe that's the reason.
So can you say again slowly? So how do I do it?
So if while you share your screen, there is an option that allows you to share your computer's audio. Maybe that's why we cannot hear what's happening in the video.
Share the screen, share the computer sound. Okay, try again. So in this video, I'm gonna show you how to create this work.
It's good now.
Okay, great, thank you. I have no idea. Okay, so in this video, I'm gonna show you how to create a polyhedron object using MPT toolbox. So we have 4 options that you can use to construct a polyhedron object in MPT toolbox. The first one is that you can construct a hex representation polyhedron. The second one is the V representation polyhedron. The third one is you can construct a polyhedron using the lower bound and upper bound vectors. And the last one is that you can construct a random polyhedron using a built-in function in MPT toolbox. And this random polyhedron is very useful for testing your algorithm. Okay, so let's look at the code. So in this code, I'm gonna show you how to create a two-dimensional polyhedron. Basically, here is the box. So x1 is between 0 and 1, x2 is between 1 and 2, and you can transform this for testing your algorithm. Okay, so let's look at the code. So in this code, I'm gonna show you how to create a two-dimensional polyhedron. Basically, here is the box. So x1 is between 0 and 1, x2 is between 1 and 2, and you can transform this inequality in equivalent form like this, matrix A and B, this, okay? And from this, we can get the matrix A and B describe the inequalities of a polyhedron. And because we don't have the equality part, so the equality part is going to be 0 or empty. And then you can construct the H representation polyhedron using the polyhedron object in Entity Toolbox. So the input to these objects is going to be the matrix A, B, AE, and BE. Okay. The second way is to construct a V representation polyhedron. So you can see that network have 4 vertices, right? The first vertex is 0 and 1 here. The second one is 1 and 1 here. The third one is 0 and 2, okay? And the last one is 1 and 2 here. So you can combine all the vertices together and then use the polyhedron class, and you specify V here as a vertex, and you put the V matrix into the polyhedron class, and you can construct a V representation polyhedron. Okay. You can also use lower bound and upper bound vectors to construct a polyhedron. So because x1 is between 0 and 1, x2 between 1 and 2, so you have the lower bound is going to be 0 and 1. The upper bound is going to be 1 and 2. Okay, and then you specify the lower bound and upper bound vector, put it into the polyhedron object, the constructor, and then you get the polyhedron object. Okay, the last one is you can use the random viewing function in Entity Toolbox to generate a random polyhedron. So here I generate random hash representation polyhedron with 2-dimensional. Okay, so these specify 4-dimensional. So let's run it. Okay, so you're gonna see that P1 is representation, P2 is a V representation, P3 is H representation, and B4 is a H representation. Okay, so to plot the polyhedron, you can use P1 plot methods. So you can see it's gonna plot a rectangle for you, or you can check that's P2 plot. So it's also the box you see, and you can check the default plot, which is the random one. So you can see it's a random 2-dimensional polyhedron like this. Okay, so that's how we can use polyhedron class to construct a polyhedron object in Entity Toolbox. Thank you. Okay, so in this video, I'm going to show you how to create. Any questions so far?
I have a quick question. When you are working with a polytope and the polytope goes by the different layers, do you conserve convexity?
What do you mean by convexity?
The convexity property, because the polyhedron holds convexity, correct?
What? I don't understand.
Yeah, so the first polytope, it's a convex.
Mm-hmm.
And do you hold the convexity across the different layers?
Why is matter?
Maybe because in the output set, you also will need to guarantee convexity.
So the output set is going to be a union of convex polyhedron, okay?
Yes.
And it's not convex. So if you just merge them together, it's not a convex set, right? As I said before, a non-convex set can be decomposed into a union of convex polyhedron, right? Using triangle, like triangulation algorithm, something like that. So
okay.
Here we only deal with convex set for each layer. And after each layer, it's gonna give you union of convex set. And then layer by layer is the number of convex polyhedron. It's gonna grow up. And then finally you get the output set with which is a union of many polyhedron, something like that. And you can, when you plot it, it's not a convex, right? It's a union of convex set.
Okay, thank you for that.
Okay, so any other questions? Okay, now we're gonna move to our mapping of a polyhedron, which is very simple, but I still put it in a video for you to be able to use it. To do offline mapping for a polyhedron. So an offline mapping of a polyhedron is defined based on an offline mapping matrix W, okay, and an offset vector B. So basically, if you have a polyhedron B, then the offline mapping of that polyhedron is P1 is equal to W times P plus B. Okay, just that simple. So let's look at the code here. So suppose I generate a random two-dimensional polyhedron, H representation polyhedron, and then I have the mapping matrix W, and this is the offset vectors. Okay, you can see that from two-dimensional, I map this polyhedron into a three-dimensional state. Okay, and then the mapping is P1 equal to W times P plus B, and then you can plot the figure. So let's see. Oh, sorry. This is an error here. So you can see that you have two-dimensional polyhedron here, and then you map these two-dimensional polyhedron in three-dimensional state. You can see it here. Okay, so that's how you do a fine mapping for a polyhedron. Okay. To do a fine mapping. Now we do intersection of two polyhedron. So in this video, I'm gonna show you how to do intersection between two polyhedron. Okay. So we random generate the first polyhedron P1 and the second polyhedron P2, and then we get the intersection between two polyhedron using this function, like the intersect function. Okay. And then we're gonna plot the figure. So we first plot the first polyhedron with red color, and then we plot the second polyhedron with blue color, and then we plot the intersection of two polyhedron. So let's consider it. So in this video, I'm gonna show you how to do the figure first, and then we plot the intersection of two polyhedron. So let's consider it. So you can see here that the intersection between two polyhedron is the yellow one. Okay. And then if you check, so you have the intersection is another polygon with 7 vertices. Okay. So that's how we do intersection between two polygons. Thank you. Okay, so any questions for the intersection?
So is intersection efficient?
So it's not. So that's the problem with the polyhedron, right? When you have a very high dimensional polytope, then the intersection and the alpha mapping is time expensive. So it's very expensive. And then that's why we come up with the idea using the star set approach to overcome these challenges. Okay. Does that answer your questions?
Yeah, thanks.
Okay, now we come up with the compact whole of two polyhedron. Okay. So in this video, I'm gonna show you how to get a compact whole of two polyhedron. So the compact whole of two polyhedron is the smallest convex polyhedron that contain two polyhedron. Okay. So first we generate a polyhedron, two-dimensional polyhedron, using the random function, and then we generate the second polyhedron. And then we get the polyunion of two polyhedron, and then we can get the convex whole of the polyunion of the polyhedron using the convex whole command in FFNN toolbox. Then we can plot the convex whole and the individual polyhedron in the convex whole. So you can see here that this is the first convex whole. This is the first polyhedron in the convex whole, and this is the second one. So the convex whole is going to be the smallest polyhedron that contains both polyhedron. Okay, so that's how we can use RMBT to get a convex whole of two polyhedron. Thank you. Okay. Questions so far? No. Okay. So in this video, I'm sorry. So here is another very important methods you need to use for reachability analysis of feedforward neural network. Okay. How to find smallest box contents in a polyhedron. So when we compute the reachable set of a neural network, there are the case that we need to compute the lower bound and upper bound vector of a polyhedron. That means we need to compute the smallest box that contains a polyhedron. And in this video, I'm going to show you how to do it. So first, I randomly generate a two-dimensional polyhedron here, P1. And then to get the lower bound and upper bound vector of this polyhedron, you use the method called outer approach here. Okay, so we use P1 outer approach, and then you can accept the lower bound and upper bound vector of this polyhedron by using P1 dot internal dot LP and P1 dot internal or UP. So to visualize that box, we can construct another polyhedron called P2 using the lower bound and upper bound we get. Okay, and then we can plot the figure. So we plot the box first, and then we plot the polyhedron which inside the box. Okay, so you can see that this is the polyhedron, and then this is the box, the smallest box that contains the polyhedron. So this is how we use MBT toolbox to get the box, the smallest box contain a polyhedron inside. Okay, thank you. Okay, so so we have time for last two methods. So when we check emptiness and boundness of a polyhedron, it's very simple. So after you compute the reachable set of a neural network, you want to check a reason about the property of the network. So in that case, you need to check if the reachable set intersect with some unsafe regions or not, for example. So when you get the intersection, then you need to check if that intersection is empty or not. So if it is empty, then that means the reachable set doesn't reach the unsafe region and the system is safe. Something like that. Okay. So in that case, we need to be able to check the empty niche or the bounded niche of a polyhedron. So you can do it by using these empty methods, empty set methods, or is bounded method. So in this case, you can see that I randomly generate a polyhedron, and then when I check if it's empty or not, it's gonna give you 0. That means the polyhedron is not empty. I check the boundness, so you can see that the boundness is 1. That means it's bounded. Okay. That's how we can check the emptiness and boundness of a polyhedron using MBT. Thank you. Okay, so I think that's all for today. So I already introduced you the concept of feedforward neural network. What is the concept of reachability and verification? And then I introduced you the concept of polytope, and then the core step to do computation using using polytope. And then I show you some videos that can help you to learn how to create and manipulate polyhedrons when you do reachable set computation later. Okay, so that's all for today. Any questions?
Yeah, one question, if you please. Where are you gonna be posting the lectures, the slides?
Yeah, I'm gonna post this letter now after this class, and also the previous letters. I guess I already have the video, but I haven't pushed it in the Canvas.
Yeah, okay. And regarding the material, are we gonna be using linear constraints in every reachability assessment method, or there are gonna be some more non-linear? I don't know.
Yes. So for now, we only care about linear constraint first.
Yeah,
Okay.
because
But
of the feedforward network, right?
Yes. Yes.
Okay.
Okay.
Thank you.
Other questions?
So according to the schedule, we have a coding assignment and a reading assignment due on Monday. It just says to write a summary for the assigned paper. So along with posting the paper, are you going to write like just a little bit about what you want us to do for that summary? Like,
Yeah,
hey,
so that's a good question. So actually I want you to summarize what is the core ideas of the paper, the main contribution, and what is the weakness, if you can find the weakness of the paper, right? So I think that's all about. So we're gonna care about the main contribution, the core techniques, and the weakness of that technique, and so you can write out your thought about how to improve that or something like that. Yeah, so that's what I expect. Don't write too much, okay? Just very concise. It does answer your question?
yes, thank you.
Okay. Okay, so I guess that's all for today. So Michael, can you send me an email? I'm gonna run today, but I'm gonna run now, but I'm gonna come back to your issue and fix it for you. I think there are something wrong, maybe. I'm gonna check it and let you know. That's work?
Yeah, I can just add a post to the Canvas discussion so that way, if anyone else has figured it out, they can comment. And also, if there is a solution, then everybody can see it.
Okay,
okay?
okay, okay, great, thanks.
Perfect. Okay. Thank you.
Okay, bye-bye.
Goodbye.